Okay, so now we want to consider the transformations generated by B alpha, and these transformations are known as a special conformal transformation. So this is the last transformation that we want to consider. And how many values does alpha take? So alpha takes D values. So that means there are D parameters, D different transformations, D generators, okay, that we would like to get our hands on. And if we just write down what is the killing vector for the special conformal transformation zeta alpha, so remember what I'm doing. I am looking at our general expression for the conformal killing vector that is over here. You know what? In fact, I'm going to copy it and move it downstairs so that we've got it handy. So here we are. Let's copy this. Good. There we go. Let's just move it down. We will want to refer to this. Okay. Good. Okay. Okay. So if we are looking at, let's make that maybe green. So if we are looking at the special conformal transformations, we set all of the other parameters to 0. So A alpha we set to 0, omega alpha beta we set to 0, lambda we set to 0. We keep only the B. And zeta alpha will look like x squared B alpha minus 2 B dot x, and then multiplied by x alpha. So that's the form of the transformation. Now, one thing that is interesting, well, we know that zeta alpha, the conformal killing vector, is a length. We also know that x squared is a length squared. What that means is B alpha itself must be an inverse length. And that's rather interesting. Remember that when we were looking at A alpha, this was a parameter of transformations. This was a length. Omega alpha beta was rotations and angles of rotations and rapidities of boosts, while lambda was a scaling parameter. So this was length to the power of naught. And now we find that B alpha, the parameter of the special conformal transformation, is an inverse length. Well, that's rather interesting. In fact, to understand the special conformal transformations, it is helpful to pay attention to that fact and to use that fact. And the way that we use it is we're going to introduce one more conformal transformation. So we can introduce one more conformal transformation. Now, you might be surprised to hear me say that. When we solve for the conformal killing vector, it seems that we solved for all possible conformal transformations, but that's not really true. You see, we didn't catch any discrete transformations. So this extra conformal transformation that we're going to solve for now, this is discrete. And when we say a transformation is discrete, it's not something like, say, a translation or a rotation. Translations and rotations we can build up slowly. I can translate by an infinitesimal amount. I can boost by an infinitesimal amount. I can scale by an infinitesimal amount. With a discrete transformation, you can't do that continuously. It's just boom, and the transformation's done, and you can't continuously deform it or obtain it by starting from the identity. So let me tell you what the discrete transformation is, and then we'll see why, in fact, it's discrete, why you can't build this up slowly in small steps from the identity. So this new discrete transformation is called inversion. So this is the name of the extra conformal transformation. Let's denote it by I. And the way that I acts, it takes x mu into x tilde mu, and x tilde mu is equal to x mu over x dot x. So that means x mu over x squared or equivalently x mu over x alpha, x alpha. Let's see if this really is a conformal transformation. So if it is a conformal transformation, well, we know what equation it has to satisfy. Eta mu nu dx tilde mu dx alpha dx tilde nu dx beta should just be some scaled version. So we wrote this as omega of x squared times by eta alpha beta. So is that equation satisfied? If it is, then we do indeed have a conformal transformation. Now, if I take d by dx alpha acting on x tilde mu, what is this equal to? Well, this is d alpha acting on x mu over x dot x. And what is this equal to? Well, the d alpha acting on the x mu gives me a delta mu alpha over the x dot x. But now I shouldn't forget that I can differentiate that 1 over x dot x. If I do, I will get a minus, because it's 1 over x dot x. I will get x dot x squared. And then I need to differentiate the two, the x dot x. If I differentiate x dot x, I'll get a 2x alpha. And let's not forget the x mu. So this is what the answer is for this derivative. Now let's plug it into the above equation and see if this really is a conformal transformation. So we will have eta mu nu, then we'll have a delta mu alpha over x dot x minus 2 x mu x alpha over x dot x squared into delta. Now it will be a new beta over x dot x minus 2 x nu x beta over x dot x squared. And again, we multiply these out according to the usual rules. Okay, so let's multiply the first term in the first bracket with the first term in the second bracket. So if we multiply these out, what do we get? Well, we'll have a 1 over x dot x squared. And then the delta mu alpha will change the mu index into an alpha, and the delta mu beta will change the nu index into a beta. So we've got an eta alpha beta. Next, let's multiply the outer terms. So if we do that product, what do we get? Okay, so that was the blue term. Now let's work out what the red term is. Okay, now you do this slowly if you need to. Okay, I'm going to write down what the answer is. The delta mu alpha will change the metric into an eta alpha nu. The eta alpha nu acting on the x nu up will bring the nu index down and turn it into an alpha. So actually, let me change that sign. This term is a negative. So we'll have a negative. We will have 2. We'll have x alpha x beta. And then we've got x dot x in the denominator times 1 over x dot x squared. So we'll get an x dot x cubed. And that's the red term. Okay, now let's look at what happens if we multiply the second term in the first bracket with the first term in the second bracket. And now we'll end up getting minus. It's exactly the same computation. So go ahead, make sure you can get this result over x dot x cubed. Good. So we've got that term. And then there's one more term, which is when we multiply the second term in the first bracket by the second term in the second bracket. And what does that give? Well, we have got a minus 2 times minus 2. This makes it a plus 4. We've got over x dot x squared times x dot x squared. So we'll get an x dot x to the 4. And then we've got x mu up, x nu up times by the eta mu nu. Well, that'll give us an x dot x. And we've got x alpha down and an x beta down. And that is the yellow term. Now, look at this. Remarkably, if we add the second and the third terms, we get minus 4x alpha x beta over x dot x cubed, and that exactly cancels against the fourth term. So those three terms